Every map of the cosmos you have ever seen tells you the same comforting thing. The universe is spread out evenly, galaxies scattered like grains of sand in every direction, no place any more special than another. But here is what those maps quietly leave out. In 2013, 3 astronomers counted 35,000 galaxies and found something missing. Around us, in every direction, for nearly 1 billion light-years, there are about 20% fewer galaxies than there should be. We are sitting near the center of a hole in space, almost 2 billion light-years across. It has a name now, the KBC void, and almost no one has been told it is there. The emptiness is so large that our own physics says it should not exist, and it may be quietly bending the numbers we use to measure the entire universe. From in here, the cosmos appears to expand faster than it truly does, and our most trusted equations have started to disagree with themselves. So the real question is no longer whether the universe is strange. The question is whether we can trust anything we see from the bottom of the hole. Get comfortable, hit subscribe if you are new here, because by the end of this, the empty sky above you will feel like the most important thing in the universe. Now, let's slowly ease into this. Part 1. The hole you are falling through. Right now, without feeling anything at all, you are moving through one of the emptiest places in the entire universe. You are sitting still, or so it seems. The floor is solid beneath you, the night outside is quiet, and nothing about this moment suggests motion. And yet you, and your chair, and your home, and the planet under all of it, and the whole slow pinwheel of 400 billion stars you belong to, are drifting through a region of space so empty that, by every reasonable expectation of physics, it should not be here at all. We have a name for it now. We did not always. For almost the entire history of our species, nobody had the faintest idea that our cosmic address was unusual in any way. That changed only recently, and most people still have not been told. The region is called the KBC void, and it is roughly 2 billion light-years across. Saying that number is easy, feeling it is almost impossible. Light, the fastest thing there is, would need 2 billion years to cross from one side of this emptiness to the other. Our own galaxy, edge to edge, is about 100,000 light-years wide, and even that already takes 100,000 years to cross at the speed of light. The hollow that contains us is something like 20,000 times wider than that, and inside this enormous bubble there is simply less of everything, fewer galaxies, fewer stars. Less matter, by about 20%, spread across a sphere reaching nearly 1 billion light-years in every direction from somewhere very close to where you are sitting tonight. I want you to sit with how strange that is, because it is easy to let it slide past as just another big number. The universe is supposed to be smooth. Not perfectly smooth, of course. There are galaxies, and there are gaps between them, and that is expected. But if you zoom far enough out, the whole thing is meant to even out, like grains of sand that look lumpy in your hand and perfectly uniform from across a beach. That smoothing is one of the bedrock assumptions of modern cosmology. It is the thing that lets us write simple equations for the entire cosmos and trust the answers. And what 3 astronomers found, when they finally added up the galaxies around us, is that our particular stretch of beach has a crater in it. A crater 2 billion light-years wide, with us near the bottom. Let yourself drop into that picture for a moment, slowly, the way you might lower yourself into water. You are not standing on solid ground. You never were. You are falling gently and constantly through the middle of a hollow so large that the nearest ordinary, average density universe is 1 billion light-years away in every direction you could point. Above you, below you, behind you, ahead of you, the emptiness reaches out farther than light has travelled since long before there were oceans on Earth. There is no wall to this room. There is no floor. The few thousand galaxies scattered through the space around you are not crowding in close the way the night sky makes it feel. They are spread impossibly thin, lonely lights in an enormous dark chamber, and they are slowly drifting away from one another, and from you. You feel none of it. There is no wind in space, no sense of speed, no rush of air to tell your body that anything is moving. The stillness you feel is the most convincing illusion you will ever experience. Underneath it, you are adrift in the largest empty space anyone has ever measured, and you have been your whole life, and so has everyone you have ever known. Nothing about your daily experience prepares you for this, and that is exactly why it matters. The ground feels fixed. The sky feels like a ceiling. The universe feels like a settled, finished place that was figured out long ago by people much smarter than us. And almost none of that is true. The sky is not a ceiling. It is an opening onto a hollow we are only beginning to map. And the people who figured out where we live did it within the last decade and a half. And what they found unsettled them. The name itself almost hides how serious this is. The KBC void sounds like a piece of filing cabinet jargon, and in a way, it is. The letters are simply the initials of the three researchers who pinned it down, the way discoveries often get named after the people who happened to be looking when the pattern finally held. But there is nothing small or bureaucratic about what those three letters point to. They point to the possibility that the patch of cosmos we have always treated as ordinary, the patch from which we have measured everything we think we know about the universe, is one of the largest and emptiest structures ever found. And we are not at its edge, where we might shrug it off as a neighbour. We are well inside it, surrounded on all sides. Here is the thought that turns this from a curiosity into something genuinely disorienting, and it is the thread we are going to follow all the way through tonight. If you grew up inside an unusual place, you might never realise it was unusual, because it would be the only place you had ever known. A person raised at the bottom of a valley, who had never once climbed out, might reasonably assume the whole world tilted gently upward in every direction, because from where they stood, it does. Now imagine that the valley is 2 billion light-years wide, and that you cannot climb out of it, not in 1,000 lifetimes, not in the lifetime of your civilization, and that every measurement you have ever made of the wider universe was made from down inside it. How would you know which of your discoveries were true everywhere, and which were only true here, in the hollow? That is the quiet, vertiginous question at the centre of all this. We did not measure the universe from a neutral place. We measured it from inside a hole. And one of the things you slowly come to suspect, as you follow the evidence, is that the universe we think we have measured may not be quite the universe that is actually out there. It may not be what it seems. Not because anyone lied, and not because our instruments are broken, but because the view from the bottom of a crater is, unavoidably, the view from the bottom of a crater. We are going to take the long way around this, the patient way, because it deserves patience. We are going to go back to the night the galaxies first came up short, and meet the people who noticed. We are going to find out what a void actually is, because it is far stranger than just empty space. We are going to learn the hidden architecture that the entire universe is built on, an architecture almost nobody pictures correctly. We are going to find our own address inside the emptiness, and discover how fast we are really moving. And then we are going to follow the consequences, one by one, into the strangest crisis in modern cosmology, a crisis about how fast the universe is growing, how old it is, and whether our home has been quietly bending those answers the entire time. To get a sense of just how thin this emptiness is, it helps to shrink it down to something you can hold in your hands. Imagine the entire cosmos compressed until an average galaxy is the size of a single grain of sand. In a normal patch of the universe, those grains would still be spread far apart, perhaps a few feet from one another, a sparse but recognizable scattering. Now step into our hollow. Here the grains thin out further still, the gaps between them widening by a fifth and more, until you could walk a long way through the dark before your hand brushed against the next one. That is the texture of where we live. Not a beach of sand, but the lonely outer edge of one, where the grains grow scarce and the spaces between them open up into something close to nothing. What unsettles me most is not the size of it, but the silence with which it kept its secret. For thousands of years, every astronomer who ever lived looked up into this hollow and saw a sky that seemed full, because they had nothing to measure it against. The emptiness does not announce itself. It does not press on you, or whisper at the edge of your vision, or cast any shadow you could notice. It simply surrounds you, patient and complete, while your senses insist that the ground is firm and the night is perfectly ordinary. Almost no one told us, because almost no one knew, and the not knowing was never really ignorance. It was the plain impossibility of seeing the shape of a room from a single fixed point on its floor. For now, though, just stay with the feeling of where you are. You are inside the void. You always have been. The night sky you have looked up at your whole life, the one that feels so full, is actually one of the most sparsely populated views available anywhere in the cosmos, and you have simply never had anything to compare it to. The first real question, the one that took us thousands of years to even know how to ask, is almost embarrassingly simple. If we are sitting at the bottom of a crater this enormous, and we cannot feel it, and we cannot see its far walls, then how on earth did we ever find out it was there at all? Part 2. The night the galaxies came up short. The discovery did not arrive with an explosion or a headline. It arrived the way most of the deepest shifts in our understanding arrive, as a small wrongness in a column of numbers that would not go away. In the year 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, set out to do something that sounds almost dull. They wanted to count galaxies, not a few of them, but tens of thousands, carefully, across an enormous span of sky and a great range of distances, building up a kind of census of how much matter sits in our part of the cosmos and how it is arranged. It is the sort of patient, unglamorous work that quietly underpins everything else. You cannot understand the universe until you have counted what is in it. To count galaxies properly, you have to know not just where they are on the sky, but how far away each one is, because 2 galaxies that look like next-door neighbours might in truth be separated by billions of light-years, one of them simply much farther behind the other. So the team pulled together measurements across a huge volume of space, reaching out across billions of light-years in every direction, and they began adding up how many galaxies fell within each shell of distance around us. They were measuring the density of the universe, layer by layer, the way you might count the rings of a tree to learn its history. And the numbers came back wrong, not wildly wrong. Not the kind of wrong that makes you suspect a broken telescope. They came back quietly, persistently, structurally wrong, in a way that is far harder to dismiss. Everywhere they looked near us, in every direction they pointed, there were fewer galaxies than there should have been. Not a few percent fewer, which you could shrug off as the ordinary lumpiness of the cosmos. About 20% fewer. And the shortfall did not stop at the edge of one cluster or one gap. It stretched outward and kept stretching for nearly 1 billion light-years before the count finally climbed back toward normal. Around us, in all directions, the universe was thinner than the rules said it had any right to be. Picture the room where work like this actually happens, because it is not what the drama of the result might suggest. There is no observatory dome, no eye pressed to a great lens. There is a screen, and a chair, and a quiet hum, and a researcher looking at a plot that should be boring. The expectation is a flat line, more or less. Count the galaxies in each shell of distance, divide by the volume, and the density should hover near the cosmic average, wobbling a little from place to place, but holding steady overall. That is what the textbook says. That is what 100 careful assumptions predict. Instead, the near shells sag. The line dips below where it should sit and stays there, shell after shell after shell, a low plateau that does not lift until the distances grow enormous. The first reaction to a result like this is never excitement. It is suspicion of yourself. You assume you have made a mistake. You check the calibration. You check whether some faint galaxies are being missed near the edges of the survey, which would fake a shortfall. You swap in a different catalogue, gathered by different people with different instruments, and you run it again. The dip is still there. You look at a completely different patch of sky, in case one direction is throwing things off. The dip is still there, in that direction too. Slowly, the suspicion turns around. The problem is not in the analysis. The problem is in the universe. The thinness is real. That is the moment a piece of filing cabinet jargon was born, and with it a small revolution in how we picture our place in things. The region they had mapped, this underdense sphere with us inside it, got tagged with the initials of the 3 people who had measured it, and so it became the KBC void. The name is modest. What it describes is not. They had found that our galaxy and our local group of galaxies and a great deal of space around us all sit inside a bubble where matter is significantly scarcer than the cosmic norm, a bubble so large it dwarfs essentially every other structure we had ever catalogued in our neighbourhood. I want to be careful here because the word void does a lot of misleading work. A void is not a vacuum. It is not a clean, scooped-out nothing. The KBC void still contains galaxies. It still contains clusters of galaxies. It even contains, as we will see later, an entire supercluster, a structure of 100,000 galaxies that we are part of. The void is not empty in the way a sealed jar is empty. It is underdense. It is a region where, when you average everything together across those enormous distances, you find roughly a fifth less matter than a fair sample of the universe should hold. Think of it less as a hole punched clean through the cosmos, and more as a desert. A desert is not lifeless. It has its scattered plants and its rare animals. But compared to a forest, it is conspicuously, definitionally thin, and you know a desert when you cross into one. We are, it turns out, living in the middle of one of the largest deserts ever found. What makes this finding land so hard is that it was not what anyone was hunting for. Keenan, Barger, and Cowie did not set out to prove we live somewhere strange. They set out to do careful bookkeeping, to measure the ordinary density of the local universe, and the bookkeeping refused to balance in the most interesting possible way. That is often how the real surprises come. Nobody is looking for them. Someone is simply trying to get an honest count, and the honest count turns out to mean something nobody expected it to mean. And almost immediately, the implications start to crowd in, which is what we will spend the rest of our time tonight slowly unpacking. Because if you have just learned that your entire neighbourhood is underdense across 1 billion light years, you cannot stop at, how interesting. You have to ask the harder follow-up. We measure the whole universe from in here. We point our telescopes outward from inside this thinned-out bubble, and from those measurements we have built our numbers for how fast the cosmos is expanding, how old it is, what it is made of. If our neighbourhood is not a fair sample, if it is one of the emptiest places around, then every one of those measurements has to be asked a quietly terrifying question. Are we seeing the real universe, or are we seeing the universe as it looks from the bottom of a desert? It is worth lingering on how a discovery like this actually feels from the inside, because it is nothing like the triumphant moment we imagine. There is no single instant of revelation, no shout across the room. There is instead a slow erosion of disbelief. The first time the count comes back low, you assume you have misconfigured something. The second time, with a different catalogue gathered by different people, you start keeping a careful list of everything that could possibly be fooling you. You worry most about the dullest culprit of all, the chance that your survey is simply missing faint, distant galaxies that are really there, but too dim to register, which would fake a shortfall out of pure incompleteness. So you correct for it, generously, bending over backward to give those missing galaxies every benefit of the doubt. And still the dip refuses to fill in. Only after every ordinary explanation has been tried and discarded does the strange one finally earn the right to be taken seriously. The tool that made any of this possible deserves a moment of respect, because it is the same tool that revealed the entire architecture of the cosmos. When light leaves a distant galaxy, the expansion of space stretches that light during its long journey to us, shifting its color toward the red. The farther the galaxy, the longer the journey, and the more its light is stretched. By measuring that stretch, astronomers can turn a flat smear of dots on the sky into a true three-dimensional map, reaching back across billions of light years. It was this patient method, applied to tens of thousands of galaxies, one at a time, that let 3 researchers do something nobody had quite done before, which was to weigh our entire cosmic neighborhood and discover that it came up light. The 3 researchers had handed cosmology a gift and a problem in the same paper. The gift was a new and startling fact about where we live. The problem was that the fact would not stay politely in its corner. It reached out and put its hand on nearly every other number we thought we had nailed down. Before we can follow it there, though, we need to understand the void itself far more intimately, because almost everyone, including most people who have heard the word, pictures it completely wrong. The emptiness around us is not simply less crowded. It behaves differently. Gravity works differently inside it. Time, in a sense, runs differently through it. And the question of what a cosmic void is actually made of has an answer far stranger than nothing. Part 3. What emptiness is actually made of. The word emptiness is one of the most misleading words in all of astronomy, and a cosmic void is where its disguise comes off. When you hear that we live inside a void, your mind almost certainly reaches for the idea of pure nothing, a clean black gap with absolutely nothing in it. That is not what is out there. The space around us, thinned out as it is still threaded with the most important and most mysterious ingredients in the universe. It is just that those ingredients behave very differently when the ordinary matter grows scarce. To understand where we live, you have to understand that emptiness, on this scale, is not an absence. It is an environment with its own rules, and those rules are not the ones we are used to. Start with what is actually present in a void. There is still dark matter, the invisible substance that makes up the overwhelming majority of all the matter in the cosmos. Dark matter does not give off light or absorb it, so we cannot see it directly, but we feel its gravity everywhere, and even inside a void it is there, just spread thin at perhaps 15% of the cosmic average density. There are still occasional wisps of hydrogen gas, the raw material that stars are made from, drifting in long, faint filaments. There are still scattered galaxies, fewer and farther apart than elsewhere, often smaller and quieter than their crowded cousins. And there is something else, something that fills every void to the brim and turns out to run the place. There is dark energy. Dark energy is the name we give to whatever is causing the expansion of the universe to speed up rather than slow down. We do not know what it is. We know that it behaves like a pressure built into space itself, a gentle outward push that exists everywhere, in every cubic foot of the cosmos, and crucially, it does not thin out when matter does. In a crowded place like a galaxy cluster, gravity from all that piled up matter is strong enough to fight the push and win, holding everything together against the expansion. But in a void, where matter is scarce, there is not enough gravity to put up that fight. And so the quiet outward push of dark energy stops being a minor background effect and becomes the dominant force in the room. This is the first strange rule of emptiness. In the void, the weakest, most ignorable force in everyday life takes charge, simply because nothing else is strong enough to oppose it. The consequence is something genuinely counterintuitive. Voids expand faster than the rest of the universe. Everything is expanding, yes, but inside a void, the dark energy wins its tug-of-war so decisively that the emptiness grows like a slowly inflating bubble, pushing its own boundaries outward into the surrounding walls of galaxies. And here is the part that should make you sit up. The process feeds on itself. The more a void expands, the more thinly its matter is spread, and the more thinly the matter is spread, the more completely dark energy dominates, and the faster the void grows. Emptiness, once it gets started, breeds more emptiness. A void is not a static gap that happens to have fewer galaxies in it. It is an active, accelerating, self-reinforcing engine of expansion, and we are sitting inside one of the largest such engines ever found. This is also where you first meet a number that will follow us all the way to the end tonight. When astronomers add up the whole universe and ask how its volume is divided, the answer is staggering. Voids occupy roughly 90% of the volume of space. 90% of space is hollow. The galaxies, the clusters, the glowing structures we think of as the universe, all of it is crammed into the remaining tenth, strung along walls and threads that wrap around the great empty bubbles. We picture the cosmos as a sea of stars with some gaps in between. The truth is almost exactly inverted. The cosmos is mostly gaps, with some stars strung around the edges, and the emptiness is not the exception. The emptiness is the main event. The strange behavior of voids reaches even into how light moves through them, and this turns out to matter enormously, because it gives us a way to see voids that has nothing to do with counting galaxies. When a ray of light passes through a region of denser than average matter, the gravity there tugs on it in subtle ways. When light passes instead through a void, it feels less gravity than it would in normal space, and because the void is also expanding while the light is crossing it, the light comes out the far side, carrying slightly less energy than it went in with. Less energy means a slightly cooler, slightly redder signal, so light that has crossed a great void arrives a touch colder than light that has not. We can actually measure this. When we look at the faint afterglow of the early universe, the oldest light there is, we find that the directions where we already know there are large voids show up very slightly cooler by around 10 millionths of a degree, exactly as this picture predicts. The voids leave a fingerprint on the most ancient light in existence, and the fingerprint says, something thin and enormous sat in the way. This is why voids are not boring. For a long time, astronomers treated them as the dull, negative space between the interesting structures, the gaps you skip over to get to the galaxies. We now understand they are almost the opposite. A void is the one place in the universe where dark energy rules without competition, which makes it the cleanest natural laboratory we have for studying the most mysterious force in physics. If you want to understand the push that is driving the entire cosmos apart, you do not study it where gravity is busy fighting back. You study it where gravity has already lost. You study it in the emptiness. And the largest, closest, best-positioned emptiness available for that study is the one we happen to live inside. So hold these new facts together, because they change the meaning of our address. We are not floating in a passive gap. We are inside an accelerating bubble where the dominant force is the same strange pressure that is tearing the whole universe apart, where the matter is thin enough that the ordinary rules bend, and where even passing light is quietly cooled by the crossing. 90% of the cosmos is built of regions like this. We just happen to be near the center of an unusually large one. And every time we point a telescope outward to measure the universe, the first thing that light has to do is climb up out of our particular hollow before it ever reaches us. To feel how completely dark energy takes over in a place like this, It helps to remember how feeble it is everywhere else. In your kitchen, in the solar system, even within the body of a galaxy, the outward push of dark energy is so utterly overwhelmed by ordinary gravity that it might as well not exist. It takes the scale of the entire cosmos for its gentle pressure to add up to anything noticeable at all. But strip away the matter, thin the galaxies until they are scarce, and that same feeble push suddenly has nothing left to oppose it. The void is the one arena where the weakest influence in the universe steps forward and takes command, simply because everything stronger has been spread too thin to fight back. There is a strange momentum to this that makes voids feel almost alive in their behavior. As a void expands and empties, it loses what little ability it had to hold itself together, and so it empties faster, and so it expands faster still. The galaxies that remain inside are slowly herded toward the edges, drawn out toward the denser walls, leaving the interior even more barren than before. A void does not sit quietly as a fixed gap. It hollows itself out over billions of years, a slow and patient deepening of its own emptiness, and the largest voids we see are simply the ones that have been at it the longest. Ours, then, is not only enormous, it is old and still working, still scooping itself emptier as we drift inside it. That last fact is the one that will not leave us alone, and it deserves to be stated plainly before we go any further, because it is the emotional center of this entire story. We have always assumed our instruments were the thing that could fool us, and so we have made our instruments astonishingly good. But there is a kind of error no instrument can fix, the error of standing in the wrong place. We are not measuring the universe incorrectly. We are measuring it correctly, with exquisite care, from inside a hole, and the view from inside a hole is, unavoidably, a hole's-eye view. The question that follows from that is the one that has thrown a quiet shadow over modern cosmology, and we are nearly ready to face it directly. But first we have to ask how a hollow this enormous could possibly come to exist, because by the ordinary rules of how the universe builds itself, a void this large should be very nearly impossible. Part 4. A desert that should not exist. There is a reason the KBC void makes cosmologists uncomfortable, and it has nothing to do with its size alone. It has to do with the fact that, according to our best and most successful theory of how the universe assembles itself, a void this large and this empty should almost never happen. Ours is not just big. Ours sits at the far, ragged edge of what the rules allow, and possibly beyond it. To feel why, you need to know how structure is supposed to form, and we will go into the beautiful details soon, but the short version is this. The universe began very nearly smooth, with only the faintest ripples of higher and lower density scattered through it, differences of about 1 part in 100,000. Gravity then spent billions of years amplifying those ripples. Slightly denser regions pulled in more matter and grew denser still. Slightly emptier regions lost their matter to the greedy dense ones and grew emptier still. Run that process forward, and you naturally get a universe with clumps and gaps. You get small voids easily, because small ripples are common. You get medium voids less often. And you get enormous deep voids only very rarely, because they require an unusually large and unusually smooth initial dip in density, the kind of starting condition that the random ripples of the early universe almost never produced. So cosmologists do something clever. They build entire universes inside computers. They start with the same tiny ripples we see imprinted on the oldest light. They let simulated gravity run for the equivalent of nearly 14 billion years, and they watch what grows. These simulations are one of the great triumphs of modern science. They reliably produce the web of galaxies we actually observe, the clusters in the right places, the filaments at the right scales, the voids in the right abundance. When it comes to the ordinary range of structures, The match between the simulated universes and the real one is superb. And then you ask those same simulations a pointed question. Build me thousands of universes. Now show me how often a void as large and as empty as the KBC void appears. And the simulations struggle. They produce such a void rarely, in well under one run in 1,000, and only when the initial conditions happen to be exceptionally, improbably smooth over an enormous region. Some researchers have tried to put a sharper number on just how unlikely our home is, and the figure they arrive at is hard to even hold in your mind. By one analysis, a void of this size and depth represents something like a 10 sigma deviation from the expected density of the universe. In the language of statistics, 5 sigma already means there is less than a 1 in a million chance that a result is a random fluke. 10 sigma is so far beyond that as to be almost meaningless in ordinary terms. It is the kind of number where you would not expect to stumble across a single example anywhere in the entire observable universe, even if you searched every corner of it. And yet, we are not searching for it. We are living in it. The least probable address imaginable turns out to be the one with our name on it. When a measurement and a model collide this hard, there are only a few honest ways to react, and each of them costs something. Maybe the void is real, and we simply got staggeringly unlucky, drawing the 1 in an unthinkable number ticket in the cosmic lottery. Maybe the void is real, and is telling us that our model of how structure forms is missing something important, that the universe builds big empty regions more readily than our equations say. Or maybe the void is not quite as extreme as the first measurement suggested, and better data will soften it into something less impossible. We are going to weigh all 3 of those answers carefully before the night is over, because the choice between them is genuinely unresolved, and serious people line up on different sides of it. But none of them is comfortable. Every road out of this leads somewhere that asks us to give up an assumption we were fond of. And whichever road turns out to be right, the discovery forces a single, quiet, vertiginous question that we can no longer postpone. If we live somewhere this unusual, can we trust the measurements we have made from here? This is the moment the void stops being a curiosity about a distant region and becomes a problem about everything. Think about what we actually do when we measure the universe. We sit inside this thinned-out bubble and we look outward, and from what we see we calculate the grand numbers. How fast is space expanding? How old is the cosmos? What is it made of? Every one of those numbers was extracted from light that reached us here, at the bottom of the desert. We have always treated our vantage point as ordinary, as a fair and representative sample of the universe, because the whole framework of cosmology rests on the assumption that no place is special. But the void quietly violates that assumption. We are not in a fair sample. We are in one of the emptiest places around, and worse, near the middle of it, surrounded by the underdensity in every direction. Let me say plainly the thing this builds toward, because it is the beating center of the whole story, and once you have felt it, you cannot unfeel it. We have spent a century making our instruments almost perfect, hunting down every source of error we could name, because we assumed the danger was always in the measuring. But there is one error no better telescope can ever remove, and that is the error of where you are standing. We are not measuring the universe incorrectly, we are measuring it from inside a hole. And a measurement taken from inside a hole, however careful, however precise, carries the shape of the hole inside it. The numbers we trust most may be carrying the shape of the void, and we would have no obvious way to tell from in here. It is worth dwelling on what these simulated universes really are, because they are one of the quiet marvels of our age. Inside a computer, cosmologists plant the same faint seeds of unevenness that the oldest light reveals, and then they let an entire artificial cosmos grow, governed by the same gravity and the same dark energy we believe rule our own. They can build 1,000 of these universes, or 10,000, each one slightly different, and then walk through them like a gardener inspecting a field, asking how often this or that kind of structure appears. When they do this and go hunting for a void as large and as empty as ours, they come back nearly empty-handed. In universe after simulated universe, our hollow simply does not form. The numbers people attach to this can feel almost theatrical until you understand what they mean. To call something a 10 sigma deviation is to say that if you generated random universes for longer than the present age of the cosmos, you would still expect to wait an unimaginable span before stumbling on even one example. It is the statistical equivalent of shuffling a deck and dealing the same perfect hand again and again and again. And the unsettling part is not that such a thing is impossible, because rare things do happen somewhere. The unsettling part is that the rare thing happened to us here, in the one place we have to live and measure from, at exactly the moment in history when we finally developed the precision to notice it. That coincidence is what gnaws at people. It is one thing to accept that, somewhere in a large enough cosmos, a freak structure might occasionally form. It is quite another to find yourself sitting inside it, holding the measuring tape, and to realize that your improbable address might be quietly rewriting the very numbers you trust most. A lottery ticket that wins is suspicious enough. A lottery ticket that wins and then changes your reading of the entire universe is the kind of thing that makes careful people deeply uneasy. For a long time, that was a philosophical worry, the kind of thing you could raise at the end of a talk and then move on from. It is not philosophical anymore. There is now a concrete, measurable 5 sigma crisis sitting at the center of cosmology, a place where two of our most careful measurements of the universe flatly refuse to agree with each other, and the void offers an unsettlingly neat explanation for why. To understand that crisis, though, and to judge whether a void could really cause it, we first need to see the universe as it actually is at the largest scales. We need to stop picturing a scattered sea of stars and start seeing the hidden architecture that everything, including our impossible desert, is woven into. Part 5. The hidden architecture of everything. If you could pull back far enough to see the entire universe at once, you would not see a scattering of galaxies sprinkled evenly through space like stars across a clear night. You would see something far more organized and far stranger. You would see a structure that looks unsettlingly alive. Galaxies are not strewn at random. They are strung along immense glowing threads, threads that cross and tangle and meet at bright knots, with great dark hollows sitting in the spaces between. The whole thing resembles a sponge, or a foam of soap bubbles, or the branching pattern of neurons in a brain. We call it the cosmic web, and it is the largest structure that exists. Everything we have been talking about, including our impossible desert, is simply one cell inside it. The architecture has a few basic pieces, and it helps to name them. At the meeting points, where several threads cross, sit the clusters, dense knots where thousands of galaxies crowd together, bound by gravity, into the most crowded neighborhoods in the cosmos. Running between those knots are the filaments, long chains of galaxies that can stretch for hundreds of millions of light years, the cables that hold the web together. Where filaments spread out and flatten, they form walls, enormous sheets of galaxies. And in the spaces enclosed by the knots and threads and sheets lie the voids, the great hollow bubbles that take up most of the room while holding almost none of the matter. This is the true shape of the universe, not a sea of stars with gaps, but a web of matter wrapped around an immense froth of emptiness. The galaxies are not the structure. The galaxies are just the bright paint that happens to mark where the web runs. For most of human history, we could not see any of this, and the reason is worth pausing on, because it shows how recently our picture of the universe snapped into focus. When you look at the night sky, you see only directions, not distances. Two galaxies can sit side by side in your telescope, and be billions of light years apart, one far behind the other. To map the web, you need to know how far away each galaxy truly is, and that information was nearly impossible to gather in bulk until astronomers began systematically measuring redshifts, the slight stretching of a galaxy's light caused by the expansion of space carrying it away from us. The more its light is stretched toward the red end of the spectrum, the farther away it is. Starting in the 1970s and 1980s, astronomers began collecting these redshifts, galaxy by galaxy, and as the distances filled in, the three-dimensional shape of the universe slowly emerged from the flat sky like a photograph developing. The first large voids were identified in 1978, and they came as a genuine shock. Nobody had expected emptiness on that scale. The mapping only accelerated from there. The Sloan Digital Sky Survey, which began at the turn of the millennium in the year 2000, measured the positions and distances of millions of galaxies and produced the most detailed maps of the cosmic web ever made. In those maps, the structure is undeniable. Filaments branch and twist like the veins in a leaf. Voids open up as dark bubbles, some of them 500 million light-years across. The surveys revealed structures larger than anyone had predicted, including a filament called the Sloan Great Wall that stretches something like 1.5 billion light-years from end to end. And on the opposite side of the ledger, they revealed supervoids even larger and emptier than our own, including one in the direction of the constellation Eridanus that may be close to 1.8 billion light-years across. The universe, it turned out, is organized on scales so large they strain the very assumption that it should look smooth. The obvious question is why? Why would the universe organize itself into threads and hollows rather than spreading out evenly? And the answer is one of the most satisfying stories in all of science, because it connects the largest things that exist to the smallest. The web was seeded in the first fraction of a second after the beginning. In that earliest instant, the infant universe was not perfectly uniform. Tiny quantum fluctuations, random jitters in the density of matter and energy, left some regions an almost imperceptible touch, denser than others, by about 1 part in 100,000. Those differences were absurdly small. But gravity is patient, and gravity amplifies. A region that started a hair denser pulled in a little more matter, which made it denser still, which let it pull harder, in a slow runaway that lasted hundreds of millions of years. The dense regions collapsed into the first stars, then galaxies, then clusters, then the threads connecting them. And the regions that started a hair emptier had their matter slowly stolen by their denser neighbors, draining outward until they became the voids. Every filament, every wall, every hollow, including the one we live in, grew from a whisper of unevenness in the first moment of time. We can actually see those original whispers frozen in place. The oldest light in the universe, the faint microwave afterglow left over from when the cosmos was only a few 100,000 years old, carries a map of exactly those early density differences, written as patches that are 100 millionth of a degree warmer or cooler than their surroundings. The warm patches are where matter was slightly piled up. The cool patches are where it was slightly thin. Feed that map into the simulations, let gravity run, and out comes the cosmic web we see today, voids and all. The match is one of the proudest achievements in the history of physics. It means we genuinely understand, in broad strokes, how the universe went from nearly smooth to spectacularly structured. The only place the story strains, as we have seen, is at the extreme end, where voids as large as ours are harder to grow than the standard recipe comfortably allows. The resemblance to living things is hard to shake once you have seen the maps. The filaments branch and rejoin like the veins in a leaf or the roots of a tree. The clusters glow at the junctions like knots in a net, and the whole structure has the spongy, holy look of something grown rather than assembled. It is one of the eerier facts in science that the largest structure in existence look so much like the smallest living tissue, not because they are related in any way, but because the same simple rule, a little pulling, acting on a little unevenness, produces the same branching patterns, whether you are growing a web of galaxies or a network of cells. It also took a surprisingly long time for us to trust what we were seeing, because each new survey kept revealing structures larger than the last, and there is always a worry that you are fooling yourself. When astronomers first traced filaments stretching across 1 billion light-years and more, the instinct was to doubt the data, because such things were not supposed to exist. The universe was meant to smooth out at those scales. Instead, the more carefully we mapped, the more the giant threads and giant hollows held up under scrutiny, until we were forced to accept that the cosmos is organized on scales that press uncomfortably against our cherished assumption of smoothness. Underneath all of it runs the same patient story, the one that ties a whisper in the first instant of time to the grandest architecture there is: tiny differences, gravity, and an enormous amount of time. That is the entire recipe. The denser whispers grew into everything bright. The emptier whispers grew into the hollows, and the hollows won most of the volume. When you look at the cosmic web, you are looking at the amplified ghost of the universe's first imperfections, stretched across billions of light-years, with us riding quietly inside one of the emptiest ghosts of all. So step back and take in the new picture, because it reframes everything that follows. The universe is a web of light wrapped around a foam of darkness, 90% hollow by volume, grown over billions of years from quantum whispers by the slow, patient hand of gravity. The galaxies cluster on the threads. The emptiness fills the bubbles. And we do not live on one of the bright threads, in one of the crowded knots, where a fair sample of the universe might be taken. We live out in one of the bubbles, well inside one of the largest hollows in the whole web. Knowing that, the next question becomes irresistibly specific. Not just, do we live in a void, but where in it, exactly? How far from the center? How fast are we moving through it? And toward what? To answer that is to find our true address in the universe, and the address comes with a speed attached that almost no one ever feels. Part 6. Finding your address inside the void. We are not at the center of the void, but we are close enough for it to shape everything. The best measurements place our galaxy somewhere between 200 and 400 million light-years from the void's true center. That sounds like a staggering distance, and by any human measure it is. But the void itself reaches outward for nearly 1 billion light-years in every direction, so our offset from the middle is actually small compared to the size of the hollow. We sit well inside it, with the underdensity wrapping around us on all sides. Wherever you look from here, you are looking out through a great deal of emptiness before you reach anything like a normal slice of the universe. To find our address properly, it helps to zoom outward in steps. We live in the Milky Way, one ordinary spiral galaxy. The Milky Way belongs to a small cluster of about 80 galaxies called the Local Group, dominated by us and by our larger neighbor Andromeda. The Local Group, in turn, sits within a far grander structure, mapped out and named only in the year 2014, the Laniakea supercluster, a sprawling collection of roughly 100,000 galaxies stretching across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven, which is a fitting thing to call something so large that it took until the present decade to even recognize it as a single object. And here is the detail that should stop you. All of Laniakea, all 100,000 of those galaxies, sits inside the KBC void. A supercluster containing 100,000 galaxies still counts as part of an underdense region. The void is so enormous that it can swallow an entire supercluster whole and still have room to spare. That is the scale we are dealing with. Our crowded-looking cosmic neighborhood is itself just a guest inside the emptiness. There is a smaller hollow right next to us as well, called the local void, a stretch of especially empty space, about 200 million light-years across, that sits directly against our position, and our galaxy is running away from it. Not drifting, running. The Milky Way is moving away from the local void at roughly 600,000 miles per hour, pushed by the gravitational imbalance between the empty side and the crowded side of our surroundings. That number is worth converting into something you can almost picture. 600,000 miles per hour means our galaxy travels about 167 miles every single second, somewhere around 850 times the speed of sound, covering more than 5 billion miles in a single year. I want you to feel that motion, because the not feeling of it is the whole point. You are sitting still. Every signal your body sends confirms it. The chair holds you, the room is quiet, the floor does not so much as tremble. And underneath that perfect stillness, the entire galaxy you are riding on, all 400 billion stars of it, the gas, the dust, the dark matter, the whole immense spiral, is sliding through the dark at 167 miles every second. There is no wind, because there is nothing to make wind against. There is no sense of speed, because everything near you is moving along with you, the way you feel motionless in a plane at 500 miles an hour. You will live your whole life inside this motion and never once detect it directly. The sun rises, the sun sets, the year turns, and the entire time you are being carried away from one emptiness and toward distant, denser shores at a speed that would cross a continent in under 30 seconds. The stillness is real to your senses and false to the universe. You have never once been at rest, and you never will be. That single grand motion is actually made of several pulls added together, which is part of why it took so long to untangle. We are being pushed away from the local void by the emptiness behind us. We are also being drawn toward the crowded regions ahead, falling toward the Virgo cluster, a concentration of more than 2,000 galaxies, about 60 million light-years away, at something like 250 kilometers per second. The whole flattened sheet of nearby galaxies we belong to, sometimes called the local sheet, is being evacuated from the void at around 260 kilometers per second, roughly 580,000 miles per hour. Stack all of these influences together, every push and every pull, and the Milky Way's total motion relative to the leftover glow of the Big Bang comes out to about 627 kilometers per second. We measure that grand speed directly because our motion makes the ancient light look slightly warmer in the direction we are heading and slightly cooler behind us, a lopsided pattern that tells us, unambiguously, that we are not sitting still in the universe. Now notice the small paradox hiding in all of this, because it sharpens the whole picture. How can a supercluster of 100,000 galaxies sit inside an underdense void? The answer is that density depends entirely on the scale you measure it over. The void is underdense when you average across its full enormous breadth, but it is not uniformly empty. It still contains filaments, and the filaments still contain clusters, and the clusters still contain galaxies. Structure exists at every level, nested inside structure, like rooms inside houses, inside a sparsely settled county. Laniakea is one of those settlements. It is large compared to a typical supercluster, but small compared to the void that contains it, and its presence does not cancel the void's overall emptiness, any more than a single town cancels the emptiness of a desert it happens to sit in. We are part of that town, falling outward through the desert at a speed we cannot feel. There is a hierarchy to all this motion that is worth tracing, because it shows how nothing in the cosmos truly stands still. Our galaxy falls toward the Virgo cluster. The whole region around us, Virgo included, drifts toward an even greater concentration of mass that astronomers named the Great Attractor. And the Great Attractor, with everything streaming toward it, is itself being drawn towards something larger still, the Shapley concentration, the most massive gathering of galaxies in our part of the universe, lying some 650 million light-years away. Galaxies flow toward clusters, clusters flow toward superclusters, and superclusters flow toward the great basins of gravity beyond them. We are a single drop in a current that runs inside other currents, all of it laid over the slow outward drift away from our void. Let yourself feel, one more time, how completely hidden all of this is from your senses. You are being carried by half a dozen overlapping motions at once, pulled toward Virgo, drawn toward the great attractor, streamed toward Shapley, pushed outward from the local void, and, underneath all of it, stretched along by the expansion of space itself. Not one of these motions registers in your body. The tea in your cup sits perfectly level. The floor does not lean. Every direction feels as settled as the last. And yet you are threading through a landscape of invisible valleys and distant mountains of mass, falling several ways at once, at hundreds of miles every second, and you have done so calmly through every quiet evening of your entire life. This is the part that makes our address feel less like a fact and more like a vantage point. We are not perched on a neutral platform watching the universe drift by. We are inside the flow, off-center in the hollow, moving with everything around us, and every measurement we take of the wider cosmos is taken from the back of this silent, rushing thing. That is why, where we are and how we move turns out to matter so enormously for what we believe we see. So that is our true address. We are inside the KBC void, a few 100 million light-years off its center, riding a galaxy that belongs to a small group, inside a supercluster, inside the void, all of it streaming through the dark at 600,000 miles an hour. It is a beautiful and slightly dizzying place to live. But the reason this address matters so much is not poetic. It is practical, and it is about to cause a genuine crisis. Because when you are sitting inside an underdense region, being pulled outward by the denser universe around it, that motion does something sneaky to the measurements you make of how fast everything is flying apart. It tips the scales, and the result is that two of the most careful measurements humanity has ever made, two numbers that absolutely must agree if our understanding is correct, do not agree at all. Part 7. The two numbers that refuse to agree. There is a single number that sits at the foundation of cosmology called the Hubble constant. It measures how fast the universe is expanding, how quickly the space between galaxies is stretching, and, right now, that number is at the center of the biggest unsolved argument in the field, because we have two excellent ways to measure it, and they give two different answers that stubbornly refuse to reconcile. The disagreement has a name. It is called the Hubble tension, and the KBC void offers one of the most natural explanations anyone has found for it. The first way to measure the expansion looks deep into the past. We study the oldest light in the universe, the faint microwave glow released when the cosmos was only about 380,000 years old. That light is a snapshot of the infant universe, and encoded in its tiny temperature ripples is everything we need to calculate how the universe should have expanded from then until now. Feed that ancient data into our best model, turn the crank, and out comes a prediction for today's expansion rate of about 67 kilometers per second per megaparsec. The unit sounds technical, but it just means that for every megaparsec of distance, roughly 3.3 million light-years, space stretches by about 67 kilometers every second. This is the early universe answer, derived from the beginning of time and projected forward. The second way looks at the nearby universe directly, here and now. Astronomers find objects whose true brightness they understand precisely and use them as cosmic measuring sticks. Certain exploding stars, called Type 1a supernovae, always detonate with very nearly the same intrinsic brightness. So by comparing how bright they truly are to how bright they appear, we can work out exactly how far away they sit. A particular kind of pulsing star, the Cepheid variable, does the same job on closer scales. Combine those distances with how fast each object is receding, and you measure the expansion rate straight from the local cosmos. No early universe model required. And this local method consistently gives a different answer. It comes out to about 73 kilometers per second per megaparsec. 67 from the beginning of time. 73 from our own backyard. The gap is about 9%. That may sound small enough to wave away, but it is not, because both measurements have become extraordinarily precise, with very small margins of error, and both are supposed to be measuring the same single property of the same single universe. They should land on the same number, and they do not. The disagreement has now reached what scientists call 5 sigma significance, meaning there is less than a 1 in a million chance that it is a random statistical accident. This is not a rounding error or sloppy work. It is a real, stubborn, deepening contradiction, and it means that something in our picture of the universe is genuinely wrong or genuinely missing. This is exactly where the void walks back onto the stage, because it offers a way to explain the gap without breaking physics, simply by taking our address seriously. Remember what an underdense region does to the galaxies inside it. The denser universe surrounding the void pulls outward on everything within, adding extra velocity to the local galaxies, accelerating them away from the center and away from us faster than the smooth expansion of space alone would carry them. Now think about what that does to the local measurement. When we measure the nearby expansion rate using supernovae, almost all of those supernovae sit inside our void. They are all being given that extra outward push by the surrounding matter, so they appear to be receding faster than they truly should be, and that extra speed gets folded into our calculation, inflating the local Hubble constant. We are not measuring the pure expansion of the universe. We are measuring the expansion plus the void's outward pull added together, and we have been reading the sum as if it were the whole. Here is the line we have been building toward since the very beginning, and now it stops being a metaphor and becomes a mechanism. We are measuring the universe from inside a whole. Earlier, that was an image, a way of feeling our strange location. Now it is the literal, quantitative explanation for the single biggest discrepancy in cosmology. The local number is too high, precisely because the hole we live in is pulling our measuring sticks outward, and we have been recording their inflated speed as the true rate of the cosmos. When scientists model how a void of the KBC's size and depth should affect local measurements, they find that it could boost the apparent expansion rate by close to the exact amount needed to explain the gap. The 73 we measure here, and the 67 the early universe predicts, may not be two warring facts about the cosmos at all. They may be the same fact, seen once from inside the void and once from outside it. The explanation even makes a clean prediction that we can test. If the void is inflating our local measurement, then the effect should fade as we look farther out, toward and beyond the void's edge. Measure the expansion rate using only nearby objects, deep inside the hollow, and you should get the high number. Measure it using objects far enough away that the void no longer dominates, and the number should drift back down toward the cosmic value of 67. In other words, the apparent expansion rate should shrink as we look across greater distances. And recent observations are beginning to show exactly that trend. The number does appear to come down as we reach farther out. It is not yet a settled case, because measuring distances to very remote objects is hard and the uncertainties are large. But the direction of the evidence points the way the void predicts. So we are left holding a remarkable possibility. The most famous crisis in modern cosmology, the one that has launched hundreds of papers and pitted careful teams against one another, might come down to a simple, humbling fact about real estate. We built our local measurement on the assumption that our neighborhood is typical and our neighborhood is not typical. It is a desert, and the desert is tugging on our rulers. If that is right, then the universe was never lying to us in the dramatic sense. It was only that the view from the bottom of the hollow looks different from the view anyone would get standing on neutral ground, and we mistook our view for the universe's. What makes this disagreement so hard to dismiss is precisely how good both measurements have become. These are not rough estimates, with sloppy margins that happen to miss each other. They are two of the most carefully calibrated numbers in all of science, each refined over decades, each cross-checked against independent methods, each with an uncertainty now small enough that the gap between them dwarfs the wiggle room in either one. When two such precise measurements of the same quantity refuse to meet, you cannot simply split the difference and move on. One of them is being pushed off true by something we have not accounted for, and the hunt for that something is what has turned this into a genuine crisis rather than a footnote. It helps to picture exactly what the void does to the supernovae we rely on. Almost every nearby exploding star we use as a measuring stick sits inside our hollow, and so almost every one of them is being given the same outward shove by the denser universe surrounding the void. Each one appears to recede a little faster than the pure expansion of space would carry it. Taken alone, the effect on any single star is modest. But because the shove points the same way for all of them, the small excesses do not cancel out. They add together into a systematic tilt, and that tilt rides straight into our calculation of the expansion rate, lifting it above the true cosmic value. This is the whole difference between a random error and a biased one, and it is the reason the void matters so much. Random errors wash out when you average enough measurements together. A bias does not. It survives every averaging, because it is built into the situation itself, into the simple fact that all our local rulers share the same hollow and feel the same pull. No amount of careful measuring can remove an error that comes from where you are standing rather than from how you are measuring. But the trouble does not end with how fast the universe is expanding, because that number is tangled up with another that is even more fundamental and even more disturbing to get wrong. If you change how fast the universe has been growing, you change how long it has been growing, which means you change its age. And when you follow that thread, you run straight into one of the strangest contradictions in all of science, a place where we appear to see, with our own telescopes, stars that are older than the universe they live in. Part 8. Stars older than the universe. The age of the universe is one of those numbers that feels like it should be carved in stone, and for years it has been. From the ancient microwave light, we calculate that the universe is about 13.8 billion years old, and that figure has been confirmed by several independent lines of evidence. But the age and the expansion rate are bound tightly together. A faster expanding universe reaches its current size in less time, which makes it younger. So if you take the high local expansion rate, the 73 we measure from inside our neighborhood, and you assume that it represents the true rate everywhere, the universe shrinks in age to roughly 12.7 billion years. A little over a billion years simply vanishes, and that missing billion years is not a harmless adjustment. It creates a contradiction so sharp that, if you take it at face value, it should not be possible. The problem is the oldest stars. Scattered through our galaxy, mostly bundled into dense ancient swarms called globular clusters, are stars that formed when the universe was very young. We have good ways of telling how old these stars are, and the methods do not depend on cosmology at all. They depend on the physics of how stars burn, which we understand extremely well. A star spends most of its life steadily fusing hydrogen in its core, and how long it can keep that up depends almost entirely on its mass. Heavy stars burn furiously and die fast. Light stars sip their fuel and last far longer. So if you look at a cluster of stars that all form together, you can read its age from which stars have already burned out, and which are still going. The point where stars are just now reaching the end of their hydrogen-burning lives acts like a clock hand and it tells you how long ago the whole cluster was born. When astronomers read that clock for the oldest globular clusters, they get an age of around 13 billion years, with an uncertainty of only a few 100 million. That measurement has been sharpened recently by the Gaia space mission, which pinned down the precise distances to these clusters and removed one of the largest sources of error from the calculation. The result held firm. The oldest clusters really are about 13 billion years old, and there is a second, completely separate clock that agrees with them. White dwarfs, the slowly cooling embers left behind when stars like the Sun die, fade at a predictable rate, and the coolest, faintest white dwarfs we can find have been cooling for something like 12 to 13 billion years. Two different methods, resting on two different pieces of physics, both say the same thing. The oldest objects around us are roughly 13 billion years old. Now hold the two numbers side by side and feel what happens. If the universe is only 12.7 billion years old, but it contains stars that are 13 billion years old, then those stars are older than the universe that contains them. Let that sit for a moment, because it is one of the genuinely impossible things you can run into in science. We are not talking about an abstract paradox buried in an equation. We are talking about points of light you could aim a telescope at tonight, ancient stars in ancient clusters that appear to have been burning since before the cosmos they live in began. A child can see the problem. Nothing can be older than the thing it is inside of. And yet, take the local expansion rate literally, and that is precisely what the sky seems to be showing us. This is the kind of contradiction that should make the hair on your arms stand up, because it is the universe refusing to be consistent with itself, out in the open, where we can see it. Either the stars are wrong, or the age is wrong, or our understanding of one of them is broken in some way we have not found. And the stellar ages are stubbornly robust. They rest on well-tested physics, and they are confirmed by separate methods. It is very hard to make 13 billion-year-old stars younger without breaking things we are quite sure about. So the pressure falls on the other number, the age derived from that inflated local expansion rate. And this is where the void quietly offers a way out of the impossible. Watch how cleanly it resolves. The crushing contradiction only appears if you assume the high local rate of 73 is the true rate of the whole universe. But the void hypothesis says that high local rate is exactly what we should not trust, because it is inflated by our position inside the hollow. The true global expansion rate, the one you would measure from neutral ground, is the lower number, around 67, the value the ancient light gives. And that lower rate corresponds to a universe about 13.8 billion years old, which is comfortably older than its oldest stars. The 13 billion-year-old clusters fit inside a 13.8 billion-year-old universe with room to spare. The paradox dissolves. The stars were never really older than the universe. We had simply measured the universe's age using a rate that the void had tipped too high. There is a quiet elegance in noticing which number turns out to be the odd one out. The ages of the stars come from local physics, from how nuclei fuse and how embers cool, and that physics does not care whether we live in a void. So the stellar clocks are unaffected by our location, and they point to an old universe. The early universe expansion rate also points to an old universe. The only measurement that points to a young universe is the local expansion rate, the one measurement we have specific reason to believe is being distorted by the hollow around us. When three independent witnesses agree and one disagrees, and you already know the dissenting witness was standing somewhere that warps its view, you start to trust the three. The age of the universe, read this way, is not in crisis at all. It is simply being misreported by the one instrument that is looking through the void. Let yourself stand inside that impossibility for a moment, because it is not an abstraction, it is a thing you could point at. Out in the halo of our galaxy hang the globular clusters, tight knots of hundreds of thousands of stars, among the oldest things in all of creation, and when we read their ages, we get numbers that brush right up against the age of the universe itself. These are not exotic objects glimpsed at the ragged edge of detection. They are bright, well-studied, sitting in our own galactic backyard, and they appear to have been shining since the cosmos was young. To be told that, on one reading of the numbers, these familiar ancient stars are older than the universe that holds them, is to be handed a contradiction in the plainest possible terms. It is as if you opened a family album and found a photograph of your grandmother holding her own grandmother as a baby. The astonishing part is how stubborn these stellar ages are. We read them in two completely independent ways. One reads the slow burnout of stars in the ancient clusters, watching which ones have just exhausted their fuel. The other reads the slow cooling of white dwarfs, the dim embers left when stars like the sun die, which fade at a rate we understand well. The two clocks rest on entirely different physics, and they agree with each other. Recent measurements from a mission that pinned down precise distances to these clusters only sharpened the result rather than softening it. The stars really are about 13 billion years old, and that number will not flinch. So when the contradiction appears, you are forced to ask which witness to doubt, and the answer is quietly revealing. The stellar ages depend on local physics that does not care in the slightest where we live. The early universe age agrees with them. Only the age derived from our inflated local expansion rate disagrees, and that is the very measurement we already had reason to suspect was warped by the hollow around us. The odd one out, once again, is precisely the one looking through the void, and so the void does it again. It walks up to a second impossible-looking problem and offers a resolution, not by inventing new physics, but by reminding us where we are standing. That is two of our grandest numbers, the expansion rate and the age of the cosmos, that look broken until you account for the hollow and then quietly heal. A pattern like that is hard to ignore. But a pattern is not proof, and a skeptic could fairly ask whether we are not just blaming the void for everything inconvenient. So we need to ask whether the void leaves any direct evidence of itself, any fingerprint we can point to that does not depend on this chain of reasoning. It turns out it does, and the fingerprint is written in motion. Because if we really do sit inside a hollow, then gravity itself should be behaving backward all around us, pushing outward where we expect it to pull in, and that is something we can actually go out and measure. Part 9. The gravity that pushes instead of pulls. Gravity, inside a void, does something that sounds at first like a contradiction. It pushes outward. Not because gravity has reversed, because it never does. Gravity always pulls mass toward mass. But the arrangement of matter around a void turns that inward pull into a net outward drift, and once you see how, it becomes one of the clearest fingerprints the void leaves on the universe around us. Picture a wide, shallow valley ringed by mountains. If you stand on the valley floor, gravity pulls you straight down toward the center of the earth. But the mountains around you are themselves full of mass, and they tug on you sideways toward their slopes. Now translate that into the cosmos. The void is the valley. The dense walls and filaments surrounding it are the mountains. A galaxy sitting inside the void feels the gravity of all that matter piled up around the rim, and there is far more matter outside the void than inside it. So the galaxy is pulled outward, toward the surrounding density, away from the empty center. Multiply that across every galaxy in the hollow, and you get a slow, systematic outflow, a whole region of the universe quietly draining outward toward its own walls. The emptiness in the middle is not pushing anything. It is simply that, with so little matter inside to hold on, the pull of everything outside wins. The beautiful thing is that this outflow is not just a theory. We can measure it. By tracking the velocities of galaxies around known voids, Astronomers can watch the pattern directly, and it is exactly what the valley picture predicts. Galaxies near the centers of voids are moving outward faster than the smooth expansion of space alone can account for. The closer to the empty center, the stronger the outward drift, weakening as you approach the denser edges. Our own galaxy is part of this pattern, which is why we are racing away from the local void at 600,000 miles per hour. We are a marble rolling up and out of the valley, pulled toward the distant mountains of matter that ring our hollow. This same effect shows up on a larger scale as something astronomers call bulk flows, and the numbers here are where the standard picture starts to strain. In a smooth, uniform universe, the random motions of galaxies should mostly cancel out when you average over a big enough region. For every galaxy drifting one way, another should drift the opposite way, so that across a few 100 million light years, the average motion settles close to zero. That is what homogeneity demands. Instead, when we measure the real universe, we find enormous coherent flows. Across regions, stretching out to 250 or 300 million light years, whole populations of galaxies are streaming together in the same direction at speeds reaching around 400 kilometers per second. That is roughly 4 times faster than the standard model comfortably predicts for such large scales. Something is giving entire swaths of the cosmos a shared shove, and a large underdense region pushing its contents outward is exactly the kind of thing that would do it. The bulk flows we see line up with the void picture remarkably well, both in how fast they are and in which direction they point. The void leaves another fingerprint, and this one is the cleanest test of all, because we predicted it in advance. If our high local expansion rate really is caused by sitting inside the hollow, then the inflation should fade as we measure across greater distances and approach the void's edge. Measure nearby, deep in the emptiness, and the rate should read high. Measure far enough out to escape the void's influence, and it should fall back toward the true cosmic value. This pattern has earned its own name, the Hubble bubble, the idea that we live inside a bubble of biased measurements bounded at roughly 2 billion light-years. Inside that boundary, the expansion rate reads around 73. Reach beyond it, and the measurements begin trending down towards 67. And studies tracking supernovae across a range of distances have begun to find precisely this fall-off, the apparent expansion rate quietly decreasing the farther out we look. It is the signature of a local distortion, not a universal truth, written across the depths of space in just the way the hollow predicts. Step back and see how the case has been built, because the structure of it matters. We did not simply find a void and declare it the culprit for everything inconvenient. We found a void, worked out how its gravity should behave, predicted specific consequences, and then went looking. We predicted an outflow of galaxies, and we measured one. We predicted bulk flows too large for the smooth universe model, and we found them 4 times too large. We predicted that the expansion rate should fall with distance, and the data are bending that way. Each prediction confirmed is a brick, and the wall is getting hard to argue with. The void is not a story we tell to feel better about a confusing number. It is a physical region whose effects we can chart, and the effects keep showing up where the theory says they should. It is worth being very clear that nothing about this requires gravity to misbehave. Gravity is doing exactly what it always does, pulling matter toward matter. The strangeness comes entirely from the arrangement. Because there is far more mass piled into the walls around the void than in its hollow interior, the net tug on anything inside points outward, toward the rim, and a galaxy, obeying ordinary gravity to the letter, ends up drifting away from the empty center. The marble does not roll uphill by magic. It rolls toward the only mass heavy enough to call it, which happens to lie outside the valley in every direction at once. Astronomers have turned this drift into one of their most beautiful maps. A long-running effort, sometimes called the Cosmic Flows Project, has measured the true distances and motions of tens of thousands of galaxies, and from that data built a three-dimensional chart of how matter is streaming through our part of the universe. The chart does not show random jostling. It shows great coherent rivers of galaxies, flowing together across hundreds of millions of light-years, draining away from the emptier regions and toward the denser ones, exactly the pattern a large void should carve. You can almost watch the hollow breathing out, exhaling its galaxies slowly toward the surrounding walls. The speeds are the part that will not fit the tidy model. In a smooth universe, these shared motions should fade to almost nothing once you average over a few 100 million light-years, because the pulls should arrive from all directions and cancel. Instead, they persist, and they run as fast as 400 kilometers per second, several times stronger than the standard picture allows. Whole districts of the cosmos are being shoved in the same direction by gravitational gradients that should not exist if the universe were as uniform as we assumed. A great underdense region pushing its contents outward is precisely the kind of thing that would produce them, which is why the bulk flows are read by many as one more signature of the hollow we live in. And yet, every brick in that wall makes a certain unease grow rather than shrink, because of what the whole structure implies about us. If the void is real and large and shaping our measurements, then we are living somewhere genuinely unusual, and we are near the middle of it. The more confidently we confirm the hollow, the more confidently we confirm our own strange position within it. For most discoveries, nailing down the evidence brings relief. This one brings a peculiar discomfort, and the discomfort is not really about the void at all. It is about a principle, one of the most cherished assumptions in all of physics, an idea that has guided us for centuries, and that the void seems to quietly violate. The principle is that we are not special, that no place in the universe is special, and we are about to see why the hollow we live in puts that comforting idea under more strain than almost anything else we have ever found. Part 10. The last place we thought we were ordinary. There is an assumption woven so deeply into modern cosmology that most of the time we forget it is an assumption at all. It is called the cosmological principle, and it states that the universe is, on large enough scales, the same everywhere and the same in all directions. The same everywhere means no location is special, that any patch of the cosmos, averaged over a big enough region, looks like any other. The same in all directions means the universe has no preferred axis, no up or down, no center to point at. It is a statement of cosmic humility, and it is also enormously useful because it is what allows us to describe the entire universe with relatively simple equations. If every place is like every other place, you can measure here and apply your answer everywhere. Strip that assumption away, and the mathematics of the cosmos becomes vastly more tangled, and predictions become far harder to make. The principle did not arrive out of nowhere. It is the natural endpoint of a long, humbling journey that science has been on for 5 centuries. Copernicus took the Earth out of the center of the solar system and set it in orbit around the Sun like any other planet. Later, astronomers showed that the Sun is not at the center of the galaxy, but stranded out in a quiet spiral arm. Then we learned that our galaxy is not at the center of anything, just one among hundreds of billions. Step by step, we have been evicted from every position of importance we ever claimed. The cosmological principle is the final, fullest expression of that lesson. It says not only that we are not at the center, but that there is no center, because every place is equivalent. After 500 years of being demoted, we had finally made peace with being utterly, gloriously average. And then we measured the void. Because if we sit near the middle of an underdense region, 2 billion light-years across, a region so rare that the standard model can barely produce one, then our location is not average at all. It is unusual, almost by definition. We are back, uncomfortably, to occupying a special place, not at the center of the solar system, not at the center of the galaxy, but near the center of one of the largest hollows in the observable universe. After spending 5 centuries learning that we are nowhere special, the data seem to be telling us that our address is, in fact, remarkable. You can understand why this irritates physicists at a level that is almost emotional. It feels like backsliding. It feels like the universe handing back a conclusion we worked very hard to outgrow. There are ways to defend the principle, and they are worth taking seriously rather than dismissing, because the people making them are not fools. One defense points out that the cosmological principle was only ever meant to hold at truly enormous scales, averages taken over regions several hundred megaparsecs across or larger. Our void is about 600 megaparsecs from side to side, which sits right at the edge of where smoothness is supposed to begin. Maybe, the argument goes, the universe is simply less uniform at those scales than we assumed, and a hollow this size, while surprising, does not really break the principle so much as redraw the line for where it starts to apply. The universe might just be lumpier over larger distances than the textbooks led us to expect. A second defense questions the depth of the void itself. Different teams, using different data and different techniques, do not all agree on exactly how underdense our region is. Some measurements land near 20%. Others come out closer to 10 or 15%. And the rarity of the void is extraordinarily sensitive to that figure. A 20% deficit is a near impossible 10 sigma outlier. A 10 or 15% deficit is far less shocking, unusual, but not absurd. So perhaps the early measurements overstated the emptiness, and the true void, once we nail it down with better surveys, will turn out to be just rare enough to be interesting without being impossible. This would preserve the principle, at the cost of admitting our current numbers are softer than we would like. There is even a third line of thought, stranger and more philosophical, that tries to make our location feel less arbitrary. It is a version of what is called the anthropic argument, and it goes like this. Observers like us can only exist in certain kinds of places. We need galaxies and stars and planets, and the long, stable stretches of time that let complex things evolve. Maybe those conditions arise most easily in regions that are mildly underdense, quiet enough to be stable, settled enough to last. If most observers in the universe happen to live in slightly thinned-out regions, then finding ourselves in one would not be a cosmic coincidence at all. It would be expected, the way you should not be surprised to find yourself on a planet rather than in the empty space between stars. The trouble is that this argument only works if our void is mild, and a 20% deficit across 2 billion light-years is a good deal more than mild. The anthropic reasoning can explain a gentle dip. It strains badly when asked to explain a hollow this enormous. It gets us part of the way to comfort and then leaves us standing in the open. So, look honestly at where this leaves us, because the choice is genuinely uncomfortable and cosmology has not made it yet. Either we accept that we live in a statistically extraordinary location, which means surrendering the hard-won principle that we are nowhere special, or we accept that our model of the universe is wrong in some important way, that structure forms more vigorously than our equations allow, which means rewriting physics we thought was settled. Save the principle and you sacrifice the model. Save the model and you sacrifice the principle. There is no third option that costs nothing, and the empirical core, the existence of a large local underdensity affecting our measurements, does not go away no matter which discomfort you choose. It is hard to overstate how much rests on this single assumption of sameness. Nearly every equation we use to describe the universe as a whole begins by assuming that what is true here is true everywhere, that our patch is a fair stand-in for all the others. That assumption is what lets a handful of measurements, taken from one small world, circling one ordinary star, speak for a cosmos of trillions of galaxies. Take it away. And the confident sentence, "The universe is this old and expanding at this rate," shrinks into the far more modest, "The universe near us looks this way, and we are no longer certain how far that look extends." The long history behind the principle is what makes giving it up feel like a betrayal. Each step in that history was a humbling, and each humbling turned out to be correct. The Earth really is not the center. The Sun really is stranded out in the suburbs of the galaxy. Our galaxy really is one among countless others. Every time we assumed we were special, we were wrong, and every time we assumed we were ordinary, the universe rewarded us for our modesty. So there is a deep, well-earned instinct that says we are probably ordinary yet again, that the void must be less extreme than it looks, or that smoothness simply begins at a slightly larger scale than we guessed. That instinct has 5 centuries of victories behind it, and it should not be brushed aside. But instinct is not evidence, and the data keep pointing the uncomfortable way. The honest position is that we are caught between a principle we have every historical reason to trust and a measurement we have every observational reason to believe, and they cannot both be entirely right. Either we are more special than we wanted to be, or the universe is built more strangely than we wanted it to be. There is no version of the story where nothing precious has to be given up. It is precisely because both of those options hurt that scientists have gone looking for escape routes, clever ways to explain everything we have seen without paying the full price of either. Some of those escape routes reach for new kinds of physics. Some reach for a different theory of gravity altogether. Some suggest the dark energy that fills the void is not the steady, unchanging thing we assumed. Each one tries to dissolve the paradox from a different angle, and each one, when you follow it, opens a door into an even stranger room. So let us walk through those doors, one at a time, and see where the ways out actually lead. Part 11. The Ways Out and Where They Lead. The first escape route is to change gravity itself. Our entire sense that the void is impossible rests on calculations made with standard gravity, the gravity of Einstein and Newton. But what if gravity behaves a little differently than we think on the largest scales? There is a long-standing alternative theory, first proposed in 1983 by the physicist Mordechai Milgram, called modified Newtonian dynamics, or MOND for short. It suggests that when gravitational pulls become extremely weak, as they do across cosmic distances, gravity grows slightly stronger than the standard equations predict. Milgram originally devised it to explain why galaxies spin faster than their visible matter should allow, but it has an interesting side effect. In a universe governed by this stronger long-range gravity, structure forms more eagerly. Matter clumps harder, superclusters grow richer, and voids grow larger and emptier than they otherwise could. Run the numbers, and a hollow as big as ours stops being a 10 sigma miracle and becomes an ordinary outcome. The impossibility simply evaporates, because the rule that made it impossible has been rewritten. That is a tempting door, but it opens onto its own difficulties. Modified gravity has always struggled to explain things that standard gravity handles beautifully, especially the fine details of the ancient microwave light and the way massive galaxy clusters bend the light of objects behind them. The bending we observe needs more gravity than the visible matter can supply, which is the very reason we believe in dark matter in the first place, and pure MOND has trouble accounting for it. Some researchers have tried hybrid ideas, keeping a modest amount of dark matter, often in the form of lightweight particles called neutrinos, alongside the modified gravity, hoping to get the best of both. These blended models can explain more, but they are intricate and not widely accepted. Changing gravity to make the void ordinary is possible, but it tends to break other things we were quite sure we understood. You solve one puzzle and inherit 3 new ones. A second route leaves gravity alone and questions dark energy instead. We have been assuming dark energy is a constant, an unchanging pressure built into space. But what if it has evolved over cosmic time, weaker in the distant past and stronger now. If the early universe expanded more slowly than we assumed, it would be older than the high local rate suggests, which would ease the age problem from a completely different direction. This idea is speculative, and the evidence for it is thin, but it is not ruled out, and it would be revolutionary if confirmed. It is worth noticing how many of these escape routes end in the same place, a rewriting of something fundamental. To avoid the conclusion that we live somewhere strange, we keep being driven to propose that the universe itself works in some strange new way. The strangeness does not disappear. It just moves from our address to our physics. A third route is the most deflating, and also the most responsible to check. Maybe there is no void crisis at all, and the whole thing is a measurement error. Maybe dust drifting between galaxies dims distant supernovae more than we account for, making them look farther away and faking a faster expansion. Maybe the pulsing stars we use as distance markers behave a little differently in different environments, throwing off the local rate. These are exactly the sorts of mundane mistakes that have humbled astronomers before, and teams have hunted them relentlessly. And so far, the boring explanations keep failing. The dust has been measured. The pulsing stars have been recalibrated, most recently with the help of extraordinarily sharp new telescopes. The discrepancy refuses to dissolve. The measurements appear to be solid, which is precisely why the tension is taken so seriously. If it were easy to explain away, it would have been explained away years ago. It helps to remember, in the middle of all this argument, just how genuinely empty the regions we are debating are. Imagine you could fly through the interior of a void at the speed of light. You leave the bright wall of galaxies behind, and ahead of you is a darkness that does not end. You travel for 1,000,000 years, and nothing. 10 million years, and still nothing. No star, no galaxy, only the faint, cold dark, and the occasional distant smudge so far off it offers no comfort. Tens of millions of years pass at the fastest speed the universe permits, and you have still not reached anything you could call a neighbor. Now and then, across unthinkable gulfs, a single dim dwarf galaxy drifts by, a lonely island that has spent its entire existence in this isolation, its few stars forming slowly, untouched by collision or company. There is no wind, no sound, no sense of progress, only the immense patient emptiness in every direction. This is what most of the universe is actually like. Not the crowded star fields of our imagination, but this, silence and distance, and the long dark between the threads. And our own hollow, the one we live in, is one of these, only larger and closer than almost any other we know. The void picture is even strengthened by a second hollow, one we found in an entirely different way. In the ancient microwave light, there is a famous feature called the cold spot, discovered in the year 2005, an unusually large and cold patch of sky, roughly 5 to 10 degrees across, where the temperature runs about 70 to 100 millionths of a degree below average. It is so large and so cold that random chance from the early universe should produce one in only about 2% of universes. For a while, some researchers floated genuinely wild explanations, including the idea that the cold spot was a bruise left by a collision between our universe and another one in some larger multiverse. It is a thrilling thought, and it is almost certainly wrong. When astronomers looked in that direction, they found evidence of an enormous underdense region, the Eridanus supervoid, perhaps 1.8 billion light-years across and lying around 3 billion light-years away. Light from the ancient glow loses energy crossing that expanding hollow, exactly the cooling effect we discussed earlier, and that accounts for much of the cold spot without any need for colliding universes. A second giant void, found through its fingerprint on the oldest light, confirms that voids are real, that they leave the marks we expect, and that ours is not a lonely fluke, but one member of a family of giant emptinesses. There is one more confirmation worth adding to the pile, because it arrives through a completely independent ruler. In the first few 100,000 years after the beginning, sound waves rippled through the hot plasma that filled the universe, and when the cosmos cooled and those waves froze in place, they left a faint, preferred distance stamped into the spacing of galaxies, a scale of about 490 million light-years. Because we understand the physics that set that scale, we can use it as a cosmic measuring rod laid down across the sky at every distance. And when astronomers measure with this rod, they too find the marks of our local hollow, the same outward tilt in the nearby motions, the same hint that we are sitting inside a region that does not quite match the universe at large. When a conclusion arrives through the cooling of ancient light, and again through frozen sound waves, and again through the streaming of galaxies, it becomes very hard to wave away as a quirk of any one method. It is also worth saying plainly why the boring escape route, simple measurement error, has lost so much of its credibility. For years the natural hope was that some overlooked mistake, a little extra dust here, a miscalibrated star there, would quietly close the gap and let everyone go home. Teams chased those possibilities hard, because finding a mistake would have been the easiest and most reassuring outcome imaginable. They measured the dust. They rebuilt the calibration of the pulsing stars with sharper and sharper instruments. And each time, the discrepancy survived intact. The very persistence of the tension, the way it shrugs off every ordinary explanation thrown at it, is what has driven serious people toward the extraordinary ones, toward modified gravity and evolving dark energy and the hollow we live in. And this is the quiet verdict of all these escape routes taken together. Not one of them fully closes the case, and not one of them makes the void go away. The independent confirmations keep accumulating, from the cooling of ancient light to the frozen sound wave rulers astronomers use to map cosmic distances, all of them pointing to the same picture of a large local hollow biasing what we see. Whether the final answer turns out to be modified gravity, or evolving dark energy, or simply the humbling admission that we live somewhere rare, the void itself remains standing at the center of the puzzle. Every door we open to escape, it leads into a stranger room, and every room has the void waiting in it. So perhaps it is time to stop trying to escape, and instead to follow the void forward, all the way to the end, to ask what becomes of a universe ruled by emptiness, and what that future means for anyone, including us, who has the misfortune or the wonder of living inside the dark. Part 12. Cosmic Castaways. If you want to know where all of this is heading, you only have to remember that dark energy is winning, and that it never tires. The expansion of the universe is accelerating, and that acceleration has a long, quiet, final consequence. Over the coming billions and trillions of years, everything that is not bound tightly together by gravity will be carried apart, slowly at first and then beyond all hope of contact. The voids, which already rule 90% of space, will only grow. They will expand into the surrounding walls, thinning the filaments, stretching the threads of galaxies until they snap. The great hollows will swallow more and more of the cosmos, and the bright web that laces through the dark today will fade into isolated islands, adrift in an ever-widening emptiness. The fact that began this whole story, that most of space is hollow, turns out not to be a curiosity about the present. It is a prophecy about the future. The emptiness is not the exception. The emptiness is the destination. For anything living inside a void in that far future, the isolation will be almost complete. Right now, from within our own hollow, we can still see the distant walls of galaxies that surround us, their light reaching us after journeys of billions of years. But, as expansion accelerates, the light from ever closer objects will be stretched and dimmed until it can no longer reach us at all. The horizon of what we can see will draw inward like a tightening circle. Our own galaxy and Andromeda will collide and merge in about 4 billion years, fusing into a single great elliptical galaxy. The small cluster of galaxies we belong to will draw together and then watch everything beyond it recede into invisibility. Eventually, our descendants, or whoever inherits this corner of the cosmos, will look out and see only their own merged galaxy, surrounded by a darkness with nothing in it at all. Sit for a moment with the strangest and most haunting consequence of that future, because it turns the whole story back on us like a mirror. Picture a civilization that arises billions of years from now, far inside a void, on a world circling a quiet star. They are curious, as we are. They build instruments and look outward, hoping to understand the universe. But the sky they search is nearly empty. There are no other galaxies to see, because the expansion has carried them all beyond the horizon of visible light. The ancient afterglow of the Big Bang, the very light that told us how the universe began, has been stretched and cooled until it has faded below anything they can detect. They have no distant galaxies to reveal that space is expanding. They have no afterglow to reveal that there was ever a beginning. From everything they can observe, they live on a single island of stars, surrounded by an eternal, static dark, and they conclude, reasonably, carefully, scientifically, that this island is all there is and always was. They never learn about the Big Bang. They never suspect the trillions of galaxies that once filled the sky. The truth is unreachable, not because they are foolish, but because of where and when they happen to live. Here is the thought that should follow you out of this, gently, the way the best questions do. That future civilization will be profoundly wrong about the universe, and they will have no way of knowing it, because their location hides the truth from them. And we have spent this entire night learning that our location too hides things from us. We sit inside a hollow that bends our measurements of how fast the universe expands and how old it is. We are measuring the universe from inside a hole, and the view from inside a hole carries the shape of the hole within it. So the question the void leaves us with is not really about the void at all. It is about how much of what we confidently call the universe is actually just our corner of it, seen from the one vantage point we can never step outside of. We may be more like that future civilization than we would like to admit, already partly blind and unable to measure by how much. This is what it means to be a cosmic castaway, not stranded on an island in an ocean, but adrift in a hollow in space, surrounded by an emptiness so large it shapes everything we can know, gazing out at a universe that may not be quite the universe that is truly there. And there is something I find, against all expectation, not frightening but almost peaceful in that. We have always told ourselves a tidy story, that we are ordinary observers, in an ordinary place, reading off the plain facts of a uniform cosmos. The void quietly takes that story away. It tells us instead that we are somewhere particular, somewhere strange, looking out through a great deal of darkness, doing our honest best to understand a whole from the inside of one of its emptiest parts. That is a humbler picture, and a stranger one, and I think a truer one. It is worth following that future all the way to its end, slowly, the way you would watch a fire burn down. Long after our galaxy and Andromeda have merged into a single elliptical sea of stars, that merged galaxy will drift in an emptiness that grows more complete with every passing eon. The other galaxy groups that are our neighbours today, still faintly visible now, will recede beyond reach, their light stretched until it fades from any instrument that could ever be built. Star formation will slow as the gas runs out. The brightest stars will burn through their fuel and die, leaving dimmer and longer-lived ones behind, and then those too will fade until the galaxy glows only with the cooling embers of white dwarfs and the dark hulks of dead suns. The sky will darken, not over a single night, but over trillions of years, into something close to absolute solitude. Every step of that darkening erases a piece of the evidence we once used to understand the universe. The receding galaxies that told us space expands will be gone. The ancient afterglow that told us there was a beginning will have cooled past detection. The very clues that let us reconstruct the history of everything will, one by one, slip below the horizon of the observable. The universe will still be there, immense and busy beyond the dark, but it will have drawn a curtain that no instrument inside the hollow can see past. The information will not be hidden by distance alone. It will be hidden by time and by expansion and by the simple misfortune of when one happens to be alive. That is what makes the future civilization in the void such a haunting figure and such a precise mirror. They will be careful and rigorous and completely wrong, and they will have no way of knowing it, because the truth will be physically unreachable from where they stand. We like to think we are nothing like them, that we live in a privileged, well-lit moment with the whole history of the cosmos laid open before us. But we have spent this entire night learning that our own window is narrower than we assumed, our own measurements quietly tilted by the hollow we cannot leave. So the next time you step outside and look up, remember what you are actually standing on. You are not on solid ground in a settled universe. You are riding a galaxy through the middle of an enormous hollow, falling outward at 600,000 miles an hour, surrounded on every side by a darkness 1 billion light-years deep, and the few lights you can see are the nearest survivors of a web that is slowly coming apart. Nobody told us this for almost the entire history of our species. We only just found out. And the finding does not make the universe smaller or colder. It makes it stranger and larger and far more mysterious than the smooth and finished cosmos we once imagined. We live inside a cosmic void. No one told us, for the longest time, and now we know. We are measuring a universe that may not be what it seems, from a hollow we cannot leave, and that is not a tragedy. It is simply our place, the one we were given, the one we are still learning to see. And there is a great deal of quiet wonder in that, in being a small, curious thing, awake for a little while, drifting through the dark, trying to understand the shape of the emptiness that holds us. Rest easy in it. The void is not coming for you tonight. It has been your home all along.